The Andromeda Galaxy, our nearest large neighbor. On a clear, dark night, far from city lights, you can see it with your naked eye, a faint smudge of light in the constellation Andromeda. Most people would never notice it, but that tiny patch of light is actually a galaxy containing over 1 trillion stars, spanning more than 220,000 light-years across, located 2.5 million light-years from Earth. The Andromeda Galaxy, also known as M31, is the nearest large galaxy to the Milky Way. It's the most distant object visible to the unaided human eye, and it's been observed for over 1,000 years. Yet it wasn't until the 1920s that we understood what it truly was. Not a nebula within our galaxy, but an entire galaxy of its own. A cosmic island comparable to our Milky Way. Today, we're exploring Andromeda in detail. We'll look at its structure, its properties, how it compares to the Milky Way, its remarkable history, and most dramatically, its future collision with our galaxy. This is the story of our nearest large cosmic neighbor, a galaxy we can study in extraordinary detail, revealing insights about galactic structure, evolution, and the dynamic nature of the universe. Let's journey 2.5 million light-years across intergalactic space to visit our neighbor. Discovery and early observations. The Andromeda Galaxy has been known since ancient times, though its true nature remained mysterious for centuries. The Persian astronomer Abd al-Rahman al-Sufi described it in 964 AD as a small cloud in his Book of Fixed Stars. This is the earliest known written record, though humans undoubtedly observed it much earlier. Under dark skies, away from light pollution, it's visible as a faint, fuzzy patch, unremarkable to casual observers, but intriguing to careful skywatchers. Through early telescopes, Andromeda appeared as a nebulous object. In 1612, Simon Marius provided one of the first telescopic descriptions, comparing it to the light of a candle shining through horn. The term nebula was applied, Latin for cloud or mist, but this said nothing about its actual nature or distance. In the 19th century, spectroscopy revealed that Andromeda's light showed different properties than gaseous nebulae. William Huggins in 1864 noted its continuous spectrum rather than the emission lines characteristic of gas clouds. This hinted that Andromeda might contain stars, but its true nature remained unclear. The great debate of the 1920s centered the nature of spiral nebulae like Andromeda. Were they relatively small objects within our galaxy, or island universes, separate galaxies comparable to the Milky Way? Astronomers were divided. Edwin Hubble resolved the debate in 1924. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he identified Cepheid variable stars in Andromeda. These stars have a well-known relationship between their pulsation period and intrinsic brightness. By measuring their periods and apparent brightness, Hubble calculated their distance. The result was stunning. Andromeda was approximately 900,000 light-years away, far beyond the boundaries of the Milky Way. This distance has since been refined to about 2.5 million light-years, but Hubble's conclusion was revolutionary. Andromeda was indeed a separate galaxy, and our universe was vastly larger than previously imagined. This discovery transformed astronomy. If Andromeda was a separate galaxy, so were all the other spiral nebulae. The universe contained countless galaxies, each with billions or trillions of stars. Our cosmic perspective expanded dramatically in a single observation. Structure and components. Andromeda is a massive barred spiral galaxy, similar in many ways to the Milky Way, but larger in nearly every dimension. The galaxy's disk extends approximately 220,000 light-years in diameter, more than twice the size of the Milky Way. This gives Andromeda a commanding presence in our cosmic neighborhood.
Andromeda's disk contains several distinct spiral arms traced by concentrations of young, hot blue stars, dust lanes, and star-forming regions. The spiral structure is somewhat subtle compared to grand design spirals like M51, but it's clearly visible in detailed images. The arms wind through the disk in a pattern determined by density waves, regions where stars, gas, and dust temporarily accumulate as they orbit. Andromeda's central bulge is prominent and massive, containing a dense concentration of older, redder stars. Recent observations reveal this bulge has a complex structure. High-resolution imaging shows a peculiar dual nucleus, two bright concentrations separated by just a few light-years. For years, astronomers debated whether these represented a binary supermassive black hole system. The answer appears to be more subtle. The brighter concentration is likely the true galactic center containing the supermassive black hole. The dimmer concentration is a stellar disk orbiting around it. What appears as two nuclei is actually an off-center view of a lopsided stellar distribution around the central black hole, possibly created by a past merger that hasn't fully settled. Like the Milky Way, Andromeda has a stellar halo, a roughly spherical distribution of old stars and globular clusters extending far beyond the visible disk. This halo is crucial for understanding Andromeda's formation and merger history. Stars in the halo preserve records of ancient events when smaller galaxies were consumed and disrupted, their stars scattered into the halo. Andromeda has approximately 450 known globular clusters orbiting it, significantly more than the Milky Way's roughly 150 globular clusters. These ancient, dense collections of stars formed early in galactic history and provide clues about the conditions during galaxy formation. The abundance of globular clusters suggests Andromeda underwent a different formation history than the Milky Way, possibly incorporating more satellite galaxies. Andromeda also contains substantial dust lanes, particularly visible when viewed edge-on. These dust lanes trace the spiral arms and regions of active star formation. Dust absorbs visible light, but re-radiates in the infrared, which makes infrared observations crucial for understanding Andromeda's structure. One surprising feature revealed by detailed observations is Andromeda's disk warp and asymmetries. The outer disk doesn't lie in a perfect plane, it's warped and twisted. Additionally, the galaxy shows some lopsidedness in its structure. These features likely result from gravitational interactions with satellite galaxies, particularly M22 and M110, which orbit Andromeda and gravitationally perturb its disk. Mass and stellar population. Andromeda is significantly more massive than the Milky Way, containing roughly 1 trillion stars, compared to our galaxy's estimated 200 to 400 billion stars. The total stellar mass of Andromeda is approximately 1 trillion solar masses, meaning if you added up all the stars, they'd equal about 1 trillion times the Sun's mass. This makes Andromeda the most massive galaxy in the local group, though the Milky Way is catching up in some mass estimates when dark matter is included. Including dark matter, Andromeda's total mass within its virial radius, the region encompassing the region gravitationally bound to the galaxy, reaches approximately 1 to 1.5 trillion solar masses. This dark matter halo extends hundreds of thousands of light-years beyond the visible stars, dominating the galaxy's total mass. Recent measurements suggest the Milky Way and Andromeda might be more comparable in total mass than previously thought, with some studies indicating the Milky Way could be nearly as massive or even more massive when dark matter is fully accounted for. This remains an active area of research, with different measurement techniques giving somewhat different results. Andromeda's stellar population spans the full range from ancient metal-poor stars formed over 10 billion years ago to young, metal-rich stars forming today. The disk contains a mix of ages, with younger stars concentrated in spiral arms and older stars distributed more broadly. The bulge and halo are dominated by old stars formed early in the galaxy's history. Studies of Andromeda's stellar populations reveal a complex star formation history. Unlike the Milky Way, which has maintained relatively steady star formation for most of its history, Andromeda appears to have experienced a major starburst roughly 2 to 4 billion years ago. This burst created a significant population of intermediate-aged stars. What triggered this starburst? The most likely explanation is a major merger, a collision with a substantial satellite galaxy. This merger would have funneled gas toward the galaxy's center, igniting intense star formation. Evidence from stellar streams and halo structure supports this merger scenario. Andromeda's current star formation rate is surprisingly low, only about 0.4 solar masses per year, less than the Milky Way, despite Andromeda's larger size. This low rate suggests Andromeda has depleted much of its gas supply, or converts gas to stars less
efficiently than the Milky Way. The past starburst may have consumed much of the available gas. The metallicity of Andromeda stars follows patterns similar to the Milky Way. Inner regions are more metal-rich, having formed stars more rapidly and completely. Outer regions are more metal-poor. However, detailed abundance patterns differ in ways that reflect the galaxy's distinct formation histories. The central supermassive black hole. At Andromeda's core lies a supermassive black hole, as expected for a galaxy of this size. Measurements of stellar velocities near the galactic center constrain the central black hole's mass at approximately 100 to 200 million solar masses, roughly 25 to 50 times more massive than the Milky Way's central black hole. This larger mass aligns with Andromeda's larger bulge mass, consistent with the observed correlation between black hole mass and bulge properties. The black hole is currently relatively quiescent, not actively accreting large amounts of material. If it were active, the galactic nucleus would shine brightly across the electromagnetic spectrum, classifying Andromeda as an active galactic nucleus. Instead, Andromeda's nucleus is comparatively quiet, similar to the Milky Way's Sagittarius A star. However, evidence suggests past activity. X-ray observations reveal hot gas near the galactic center, and radio observations detect emissions consistent with past energetic events. Like most large galaxies, Andromeda's central black hole likely alternates between active and quiescent phases depending on gas availability. The peculiar structure of Andromeda's nucleus, the double concentration of light, relates to the black hole's location. The eccentric stellar disk orbiting the black hole creates this asymmetric appearance. This structure might result from a past merger that disrupted the central stellar distribution without yet relaxing to a symmetric configuration. When the Milky Way and Andromeda eventually merge, their central black holes will sink toward the center of the merged galaxy through a process called dynamical friction. Eventually, they'll form a binary black hole system, orbiting each other and emitting gravitational waves. Over millions of years, gravitational wave emission will cause the orbit to decay, and the two black holes will merge in a cataclysmic collision, releasing enormous energy in gravitational waves. The merged black hole will have a mass around 100 to 200 million solar masses, making it one of the more massive black holes in the local universe. This merger will be detectable by future space-based gravitational wave observatories like LISA, though it won't occur for billions of years. Satellite galaxies. Like the Milky Way, Andromeda doesn't exist in isolation. It's accompanied by a family of satellite galaxies orbiting it. The most prominent are M32 and M110, both visible in amateur telescopes near Andromeda's core. M32 is a compact elliptical galaxy, small but dense, with a stellar mass of about 3 billion solar masses. It orbits very close to Andromeda, just 24,000 light-years from the galactic center, and its gravitational influence perturbs Andromeda's disk. M32's compactness is unusual.
It may be the stripped core of a once larger galaxy that passed through Andromeda's disk, losing its outer stars through tidal stripping. This interaction could have contributed to Andromeda's past starburst and the structural peculiarities in its disk and nucleus. M110, also known as NGC 205, is a dwarf elliptical galaxy, larger and more diffuse than M32. It orbits Andromeda at about 180,000 light-years distance, farther out and less perturbed by tidal forces. Unlike M32, M110 shows signs of recent star formation, unusual for an elliptical galaxy, suggesting complex interactions with Andromeda's environment. Beyond these prominent satellites, Andromeda has many smaller dwarf galaxies. Surveys have identified dozens of dwarf spheroidal galaxies, small, faint systems, containing perhaps only millions or tens of millions of stars. These ultra-faint dwarfs are dominated by dark matter and represent some of the least luminous galaxies known. The total number of Andromeda satellites remains uncertain. New discoveries continue as surveys become deeper and more comprehensive. The satellite population likely numbers in the dozens to possibly hundreds if we include the faintest systems. Comparing Andromeda's satellites to the Milky Way's reveals interesting differences and similarities. Both galaxies have comparable numbers of known satellites, though the distributions differ in detail. Andromeda's satellites appear to show some spatial anisotropy. They're not distributed isotropically, but show some preference for certain directions, possibly indicating they were accreted along filaments in the cosmic web. The satellite galaxies serve as tracers of Andromeda's dark matter halo. By measuring satellite orbits and velocities, astronomers constrain the total mass and distribution of dark matter surrounding Andromeda. These measurements are crucial for understanding galaxy formation and dark matter properties. Satellite interactions shape Andromeda's evolution. When satellites orbit, they experience tidal forces that can strip stars and gas, dispersing them into stellar streams orbiting the galaxy. Andromeda's halo contains multiple stellar streams, trails of stars from disrupted satellites. These streams preserve information about past merger events and help reconstruct Andromeda's accretion history. Viewing Andromeda from Earth. For observers on Earth, Andromeda is a remarkable object, the most distant thing visible to the naked eye and a prime target for amateur astronomers. Under dark skies, away from light pollution, Andromeda appears as an elongated smudge of light spanning about 3 degrees across the sky, roughly 6 times the angular width of the full moon. However, only the bright central region is visible to the naked eye. Long exposure photographs reveal the full extent of the galaxy's disk stretching across much more of the sky. The reason we see only the core with our eyes is that the outer disk is too faint. Our eyes aren't sensitive enough or capable of long exposures like cameras. But the full galaxy, if our eyes could see its entire extent, would appear 6 full moons wide, a spectacular sight. Binoculars or small telescopes improve the view dramatically. With optical aid, the bright core and hints of the disk structure become visible. Larger amateur telescopes reveal dust lanes, the locations of M110 and M32, and, with very good conditions, suggestions of spiral arm structure. Professional observations across the electromagnetic spectrum reveal far more. Optical images show stellar populations and dust lanes. Infrared observations penetrate dust, revealing star-forming regions and the galaxy's temperature structure. Radio observations map neutral hydrogen gas and molecular clouds. X-ray observations detect hot gas, X-ray binaries, and the nuclear region. Ultraviolet observations trace hot, young stars and star-forming regions. Because Andromeda is relatively nearby, we can resolve individual stars, unlike in more distant galaxies, where only the integrated light of millions or billions of stars is detectable. The Hubble Space Telescope has imaged regions of Andromeda in extraordinary detail, identifying millions of individual stars and studying stellar populations across the galaxy. The panchromatic Hubble-Andromeda Treasury Program, completed in 2013, produced a mosaic of Andromeda covering about a third of the galaxy with unprecedented resolution. This image contains 1.5 billion pixels and shows over 100 million individual stars. It's one of the most detailed astronomical images ever created and provides a wealth of data about stellar populations, star formation history, and galactic structure. From Andromeda's perspective, the Milky Way would appear similarly. An astronomer on a planet in Andromeda would see our galaxy as a faint smudge, visible to their naked eye under dark skies, spanning several degrees across their sky. They could study the Milky Way in comparable detail to how we study Andromeda. This symmetry is profound. We're each other's nearest large neighbors, mutually observable, mutually interesting. Two comparable galaxies in cosmic proximity. Comparing Andromeda and the Milky Way. Andromeda and the Milky Way are often compared as sibling galaxies, and while similar in many ways, important differences exist. Size. Andromeda is larger, with a disk diameter of about 220,000 light-years, compared to the Milky Way's 100,000. Andromeda contains more stars, roughly 1 trillion, versus our 200 to 400 billion. This makes Andromeda the dominant galaxy in the local group by stellar mass. Mass. Total mass is more ambiguous. Including dark matter, recent estimates suggest the galaxies might be more comparable than previously thought, with some measurements indicating the Milky Way could be nearly as massive or even more massive. Different measurement techniques give different results, and the exact mass ratio remains uncertain. Structure. Both are barred spiral galaxies. Andromeda's bar is less prominent than the Milky Way's, and its spiral structure is somewhat less defined. Andromeda has a larger, more massive bulge. The Milky Way appears to have more active spiral arms with higher contrast. Star formation. The Milky Way currently forms stars at 1 to 2 solar masses per year. Andromeda forms stars at only about 0.4 solar masses per year, despite being larger. This suggests Andromeda has exhausted more of its gas supply, or forms stars less efficiently. History. Andromeda experienced a major starburst 2 to 4 billion years ago, possibly from a significant merger. The Milky Way's star formation history has been more steady, without such dramatic bursts. This indicates different merger histories shaping each galaxy's evolution. Satellites. Both have comparable numbers of known satellites, though distributions differ. Andromeda has more globular clusters, 450 versus 150, suggesting differences in early formation or satellite accretion history. Metallicity. Both show similar radial metallicity gradients and overall abundance patterns, consistent with their comparable masses and types. Detailed differences in specific element ratios reflect their distinct star formation histories. Observations. We observe Andromeda from outside, seeing its full structure clearly, but unable to resolve fine details as we can in the Milky Way. We observe the Milky Way from inside, with superb detail on small scales, but difficulty mapping the overall structure. Each galaxy provides complementary perspectives. Andromeda for overall structure, the Milky Way for fine detail. In essence, Andromeda and the Milky Way are comparable large spiral galaxies with broadly similar properties but distinct individual histories. They represent the two dominant galaxies in our local group, and their eventual merger will reshape our cosmic neighborhood fundamentally. The approaching collision. Perhaps the most dramatic aspect of Andromeda is that it's on a collision course with the Milky Way. Spectroscopic measurements reveal that Andromeda is approaching us at approximately 110 kilometers per second, about 250,000 miles per hour. This motion is contrary to the general cosmic expansion. While most galaxies are receding due to the expansion of space, Andromeda and the Milky Way are gravitationally bound. They're falling towards each other, overcoming the local expansion. Computer simulations incorporating the measured velocities and the galaxy's masses predict the merger timeline. In about 4.5 billion years, the two galaxies will undergo their first close passage. They'll swing past each other, gravitationally deforming both galaxies and ejecting stars and gas through tidal forces. After the first
passage, the galaxies will separate, but their mutual gravity will draw them back. A second close passage will occur, further disrupting both galaxies. Over hundreds of millions of years, the galaxies will undergo multiple passages, losing energy through tidal interactions and dynamical friction. Eventually, roughly 6 to 7 billion years from now, the merger will be complete. The two galaxies will coalesce into a single large galaxy, likely an elliptical or lenticular galaxy. The spiral structure of both galaxies will be destroyed, the disks scrambled into a more spheroidal configuration. Astronomers have dubbed this merged galaxy Milkomeda or Milkdromeda. What will this look like from Earth? Actually, Earth and our solar system will likely survive intact. While the galaxies will collide, stars are so widely separated that direct stellar collisions are extremely unlikely. The space between stars is vast compared to stellar sizes. The Sun will pass through the merger unscathed, though its orbit within the galaxy will change dramatically. Our solar system will be flung to a different position in the merged galaxy, possibly into the outer halo, possibly into the denser inner regions. Our view of the night sky will transform completely. The familiar constellations will disperse as stellar positions shift. At the height of the merger, the night sky might be filled with dramatically disturbed galactic structures, glowing with star formation triggered by gas compression. However, there's a caveat. The Sun will have evolved significantly by then. In about 5 billion years, roughly when the merger is underway, the Sun will expand into a red giant, potentially engulfing Earth or rendering it uninhabitable. The merger of Andromeda and the Milky Way will occur as our solar system approaches the end of its habitable lifetime. For other stars in both galaxies, the merger represents a new beginning. Vast amounts of gas will be compressed, triggering intense star formation, a starburst creating millions or billions of new stars. The merged galaxy will blaze with the light of young, hot stars before gradually settling into a quieter, redder elliptical galaxy as the starburst fades. The merger will also affect the local group. M33, the Triangulum galaxy, may also merge with the Milky Way Andromeda system, or it may be ejected by the gravitational chaos. Smaller satellite galaxies will be disrupted or incorporated. The entire dynamical structure of the local group will be reshaped. Andromeda in context. Beyond its relationship with the Milky Way, Andromeda is significant as the largest and most massive galaxy in the local group and as a valuable laboratory for studying galaxy formation and evolution. The local group is a small collection of about 80 galaxies spanning roughly 10 million light-years. Most are dwarf galaxies. The three largest, Andromeda, the Milky Way, and M33, dominate the group's dynamics. Andromeda, being the most massive, exerts the strongest gravitational influence. The local group itself sits within the Virgo supercluster, a larger structure containing thousands of galaxies. The local group is falling toward the Virgo cluster, the supercluster's dense core, while simultaneously being pulled toward the Great Attractor, an even more massive concentration of galaxies beyond Virgo. Andromeda's properties make it a valuable comparison object for understanding galaxies beyond the local group. By studying Andromeda in extreme detail, we learn about processes operating in all spiral galaxies. Its resolved stellar populations inform models of stellar evolution and galaxy assembly. Its structure tests theories of spiral density waves and bar formation. Its merger history illuminates how galaxies grow through hierarchical accretion. Andromeda also serves as a testing ground for dark matter theories. By measuring rotation curves, satellite orbits, and stellar kinematics, we constrain Andromeda's dark matter distribution. These constraints test dark matter models and probe whether dark matter behaves as predicted by cold dark matter theory. The galaxy's relative proximity allows studies impossible for more distant galaxies. We can observe individual Cepheid variables, study stellar populations in detail, map the kinematics of millions of stars, trace stellar streams from disrupted satellites, and probe the galaxy's three-dimensional structure. These detailed observations provide benchmarks for interpreting observations of galaxies too distant for such detailed study. Future observations. Our understanding of Andromeda continues to deepen as observational capabilities improve. The James Webb Telescope, with its infrared sensitivity, is observing Andromeda to study stellar populations, star formation regions, and the structure of dust and gas. Infrared observations penetrate dust that obscures optical observations, revealing previously hidden structures. Radio observatories map neutral hydrogen and molecular gas throughout Andromeda, tracing the raw material for future star formation. These observations reveal how gas is distributed, where it's dense enough to form stars, and how gas dynamics couple to stellar dynamics. X-ray observatories like Chandra detect X-ray binaries, hot gas, and the nuclear region. Counting and characterizing X-ray sources provide information about stellar populations, particularly massive stars and compact remnants like neutron stars and black holes. Gravitational wave observations may eventually detect signals from binary black holes or neutron star mergers within Andromeda. While current detectors aren't sensitive enough to detect individual sources in Andromeda, future detectors might reach this capability, opening a new window on the galaxy's compact object population. Precise astronomy, measuring stellar positions and motions, is revealing Andromeda's internal dynamics in 3 dimensions. By measuring how stars move, not just their line-of-sight velocities, but also their motions across the sky, astronomers reconstruct the galaxy's gravitational field and mass distribution with unprecedented precision. Large-scale surveys continue identifying more satellite galaxies. The faintest, ultra-faint dwarfs remain to be discovered, and each new satellite provides information about Andromeda's dark matter halo and accretion history. Spectroscopic surveys obtaining spectra from millions of stars in Andromeda reveal detailed chemical abundances, ages, and kinematics. This information reconstructs the galaxy's star formation history, merger history, and chemical evolution with extraordinary fidelity. All these observations build toward a comprehensive understanding of Andromeda as a complete system, a galaxy we can study with a level of detail matched only by the Milky Way, serving as a Rosetta Stone for interpreting galaxies throughout the universe. The Andromeda Galaxy, M31, our nearest large neighbor in space, visible to the naked eye as a faint smudge, yet containing 1 trillion stars across 220,000 light-years. It's a galaxy remarkably similar to our own, yet distinct in important ways. Larger and more massive, with more stars and a different formation history. It experienced a recent starburst where we did not. It forms stars more slowly now than we do. Its satellite system and globular cluster population reveal different assembly processes. Most dramatically, it's approaching us, destined to merge with the Milky Way in billions of years, reshaping our entire cosmic neighborhood and transforming 2 grand spiral galaxies into a single elliptical. For astronomers, Andromeda is invaluable, close enough to resolve individual stars and study in extraordinary detail, yet far enough to see as a complete external galaxy, providing the outside perspective we can never have on the Milky Way. Every observation of Andromeda informs our understanding of spiral galaxy structure, evolution, and dynamics. For humanity, Andromeda represents cosmic perspective. That faint smudge visible on dark nights contains 1 trillion suns, perhaps countless planets, possibly even other civilizations gazing back at our Milky Way. The light we see left Andromeda 2.5 million years ago, when our ancestors were just beginning to use stone tools. We're seeing the galaxy as it was in the deep past.
And in the deep future, Andromeda and the Milky Way will unite, merging into a new galaxy, a monument to gravity's inexorable pull and the dynamic, ever-changing nature of the cosmos. Thank you for this journey to our nearest large galactic neighbor. If you found this exploration valuable, subscribe for more deep dives into galaxies and cosmic structures. And leave a comment. If you could visit any part of Andromeda, where would you go? Keep exploring, keep observing, and keep marveling at our cosmic neighbor across 2.5 million light-years.